Okay, so now we're going to talk about the Heisenberg uncertainty principle, and then we're going to wrap it all up, and I'm going to give you the postulates of quantum mechanics that were based initially on what Max Born suggested in 1926, and then was built on by Schrödinger. Okay, so Heisenberg uncertainty principle. You've probably heard this in popular culture, like, oh, you can't know both your speed and momentum simultaneously because we're limited in what we can measure. No. It's not that. And there's a podcast of me bitching about how it's not that. There is a fundamental limitation of what is truth. There's a difference between us knowing it and its truth. We cannot find the truth. So we cannot specify simultaneously with precision the momentum and the position simultaneously of a particle. What that means is that if I were to take, say, the position and momentum. If I were to ask a wave function, hey, wave function, what's your position? And what's your momentum? It matters which order I ask it, because me asking it one thing is going to inherently change the outcome of the other. And so from that, this is actually called the commutator. And this equals p hat x hat minus x hat p hat. Okay. And so this, whoops, did I get that wrong? I did get that wrong. My bad. Sorry. Just off by a negative sign. But so xp. So this is equal to x hat p hat minus p hat x hat. And so this commutator basically says that if I were to ask, I'll show you this way. So if I said, okay, psi x hat p hat psi, if I were to take the expectation value of this, I would get some number. Okay, so if I were to measure position first, or momentum first and then position, I would get some value. If I were to do that again with psi position first and then momentum, so I've got x operating on psi, and then I've got p operating on psi dx. If I were to do this, expectation value of x then p, expectation value of p then x. So notice that I've switched the order, x then p, p then x. If I were to take the difference of those two, okay, if there was no difference between them, I should get 0, right? I don't. I get IH bar. And that's because order matters. And from that, we have the Heisenberg uncertainty principle to where the uncertainty in the position multiplied by the uncertainty in the momentum is always greater than or equal to h bar over 2. Okay, now I'm not going to go into all of how this works. We don't have time because we need to get to spectroscopy. But I want you to take two things with you. The first thing is that this is not about the limitations of our measurements. It kind of is, but it's not the limitations of the measurements that you yourself have taken. It's not a, let me see if I have, I do. I'm going to go and I'm going to measure the height of my eraser. Yay, it's about 6.5 centimeters long. I'm going to do it again. Okay, it's about 6.51. Do it again. 6.50. Do it again. 6.5, whatever. And I, on average, get about 6.5 centimeters plus or minus 0.01, which is the uncertainty associated with this ruler. That is not the uncertainty we are talking about. No, 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 no. We are talking about a fundamental uncertainty associated with which wave function is describing the system upon the measurement. Okay, so if you think of, and this is kind of not the best way to think of it, but we're going to do it anyway. Okay, so here's a wave. It's a standing wave around a circle. And that standing wave is going to be the wave function, essentially, of an electron bound to a ring. Okay, where is the electron then, if it is a wave? It's not here, it's a standing wave. It's actually the whole place. So there's an uncertainty or a fuzziness associated with the information contained within the position. Likewise, the same with the momentum. And so to think of the Heisenberg uncertainty principle as just a limitation in what we can measure because of our instruments, it's not true. It's actually a limitation in what we can understand of a system, even theoretically. There is a limit. The Bohr biography goes into a little bit more, but know that this is what's called the commutator, and it yields our x hat, or x time uncertainty, delta x, delta p is always greater than or equal to h bar over 2. I mean, it can be equal to h bar over 2, but that's the best you're going to get. So it could equal, but most of the time it's going to be greater than. These are called coupled conjugates, or complementary, what are they called? I can't remember, but they're complementary to each other. You have the same thing with energy and time. If we were doing time-dependent quantum mechanics, we would find that the energy and the time are coupled together like this. And so if you measure the energy of a system, you can't know anything about the time, likewise, or with precision simultaneously. Likewise, if you measure something about the time, you can't know stuff about the energy. And this is important in spectroscopy, and it limits the knowledge of the time scale associated with the energy transition. Cool, so this is known as the Heisenberg uncertainty principle, and it's what we're starting from. And again, it's not about physical measurement. I mean, it is, but it's a theoretical limit of our knowledge of a system. Go team. Okay, next thing, postulates of quantum. Okay, the postulates are, number 1, all the info is contained in psi. Okay, or I should say psi of x in one dimension. You can have psi of x, y, and z, and pretty soon we're going to have psi of r, theta, and phi, r and a radius, phi an angle, and then theta the other angle. So all the information we need to know about our quantum system is contained within psi. We use the time-independent Schrödinger equation to find psi. So psi, Hamiltonian operating on psi is equal to E psi. We know what E is. We have atomic spectra. That's our observation. Okay, so what we're going to do is we know our Hamiltonian. That's just the total energy operator. And so we're going to have this, pick out this arbitrary psi. We're going to operate on it, and we're going to see if it spits out the energies that match our atomic spectra. If it does, yay, we found the wave function for our atom. If it doesn't, crap, we did not find the wave function for our atom. We got to try again. And we do this cyclic process. Luckily, we know most of the, well, we know the wave function for hydrogen. After that, it becomes an approximation because it's way too damn complicated. So, number 3, each physical property has an operator. Each physical property, i.e. an observable, has an operator. Based on x hat equals x and p hat equals I h bar ddx. Okay, oops, that should be a minus I h bar ddx. I think I may have been missing a minus sign in previous notes. You should pay attention, make sure you read Atkins. Okay, so there's an observable property, position, momentum, and it has an operator associated with it. Okay, in classical physics, momentum is mass times velocity. In classical physics, x is x. And so now momentum is the outcome of the operation on the wave function using this operator for momentum. Okay, number 4, the expectation value value of any of the observables is found by taking your operator and operating on the wave function with your operator, and then multiplying it by the complex conjugate of the wave function. And most of the time, that's going to be just multiplying it by the wave function because we're not using complex wave functions. If we were using a complex number in our wave function, you would exchange the I for a negative I. But psi times the operator operating on psi, that value multiplied by psi, integral of that is going to equal your expectation value, and that's going to be some number representative of what happens when you take a large number of observations. And number 5, psi squared dx is a probability distribution. Distribution. Psi squared is a probability density multiplied by its dimension is a probability distribution. So you got probability over volume multiplied by your volume for 3 dimensions, and that gives you your probability distribution. Go team. The 5 postulates of quantum mechanics. While you're working on your homework, recognize that this is brand new mathematics for many of you, and that's totally fine. This is kind of a wonky way of thinking of this. There is no classical analog for the majority of the work that you are doing. So if you're trying to come up with a picture of like, okay, so I know that the electron is orbiting around, stop what you're doing. You're doing it wrong. Quantum mechanics is a mathematical construct, okay? And so from that, you need to be thinking in terms of probabilities. What is the likelihood of? What is the probability of the outcome of this measurement? Okay. Go team. This is where I have a lot of students get really frustrated because you're like, I have no idea what to do. And that's okay. It takes a lot of practice. And so I think I've given you the tools that you need thus far. And so we're going to do a lot of problems in class together. Go team. Okay. Postulates of quantum. Yay. That's all I got.